So let's review what we did in the last class. So this is a typical stress-strain relation of structural steel. And this area is a linear elastic area, and then we have a almost perfectly plastic area here, and then here hardening area. So the characteristic of a stress-strain curve, this is a real strain stress curve of structural steel, can be categorized by three parts. And until now, we only focus on linear elastic part, right? Now, we wanted to expand our interest to the plastic part. So, we idealize this stress-strain relation very simply like this. This is an elastic and perfectly plastic material model. So, elastic means this area is elastic and this area is perfectly plastic. Plastic model, right? Okay, so now let me continue to talk about the elastic perfectly plastic model. This is the easiest plastic model of material. Okay? So, one-dimensional ink model. So, we can understand this elastic perfectly plastic model with a very simple device which has a spring, okay, and here force is a stress and some sliding device here. This is let's say this is a friction device. So, here we have a friction threshold sigma 0. Let me think about this behavior of this model. So here we have a spring. You know the behavior of a spring. You know behavior of a friction device? Here we have some material, we have a body here, okay? I'm going to put this body into some surface. Then between these two, there is friction, right? And so if I increase the load from 0 to some, so when the load applied is small, this body doesn't move. But if this load is bigger than some specific load, this starts to move, right? This is the property of friction device. So, the displacement from here can be considered as a strain, stress. First, I'm going to increase the stress. Okay, then only spring will be stretched, right? So due to that, the response is elastic. And once the internal stress of this spring go to the sigma 0, this friction device move, right? This will move. Okay? So, what I like to show is that the elastic perfectly plastic material model can be explained by this simple device, which has a spring and friction device, right? Okay, so now this friction device is moving. Okay, this part is moving. During this motion, okay, the stress in the spring doesn't increase, constant. Or it should be yield stress, sigma 0, right? Okay, then if I decrease, if I unload the loading, what happens? So, for example, so I'm going to, okay, so this would be better. So, initial stage, this is the initial stage. I'm going to apply sigma equal 0. And then, if I increase the loading, spring will be stretched a little bit. So it's stretched, and sigma, and this is A, B. Stage of A is here, stage of B is here, and stage of C equal C is much stretched. Okay, stage of C is here, C, and next stage D is moving. Okay. Okay, there is a movement in the friction device. This is a stage D. Okay. The phenomenon happens like this. You understand? So, next stage, if I unload DE, what happens? If I unload, the friction device is here. Okay, E will be here, E. So if I unload, totally unload after full unloading, there is a movement here, right? Permanent movement. This is a plastic deformation. We are saying this is a strain P. So actually, in the real material, inside of material, there are some structure of very atomic structure, right? It's a crystal structure. So if this crystal structure slip, this permanent deformation happen, we are saying this is a plastic behavior. Stress, strain. Yeah. let's say this is a total strain E, okay, equal elastic strain from here to here, E, let's say this is a EE, this is a plastic strain, EP. So total strain is just the sum of elastic strain plus plastic strain, right? And we know the material law. Material law is sigma equal E elastic strain. Okay, so when we use this is a relation at this stage, right? So you cannot use sigma equal E, E. This is wrong, right? This is total strain. So this relation only hold, this is only, this is right only for this part, right? So then if I put this equation into here, we can simply calculate stress E equal total strain minus plastic strain. So driving force for the stress, so the stress is only related with the elastic strain, right? Stress is only related with the elastic strain, not related with the plastic strain, okay? So this is very important. So here you need to understand the concept. Total strain can be decomposed is a sum of the elastic strain plus plastic strain, okay? And stress is only related with the elastic strain, okay? And now let me talk about energy. Strain graph. So energy can be calculated by the area of all of this, right? This is energy done by the external work. So this is a mechanical work. Done on the material. And here in this graph, let's unload. If I unload at this point, the curve will go to the here, right? Okay, so here we have a material, and I did some mechanical work on this material, right? So then I'm going to unload. Then this material, okay, will go to the undeformed shape, right? That's the elastic, right? In linear elastic, under the linear elastic assumption. But in this case, this point cannot go to this point and go to the other point. So amount of stored in the body is only this, right? Even I work much bigger amount of work, but only this part is stored. Strain energy. Elastic energy. Energy stored. Then what's the remaining thing? What happened for remaining one? So here we have a system. I gave a work 100 joule, but here this material have only 30 joule elastic energy. Only 30 joule is stored. Then the difference, 70 joule, where is it? Where is that 70 joule? It is used for plastic deformation, right? Actually, it is changed to the heat and disappear. Okay? So the difference is dissipated energy. During plastic deformation. Edge heat. Okay. So the difference is this amount of energy is difference. This is the difference. So during the plastic deformation, energy is not stored, energy is dissipated as a heat. Okay? So because of this dissipation, plastic process is not reversible. Elastic process is reversible, right? If I put the 100 joule, all the 100 joule is stored as a strain energy, right? But in plastic process, that doesn't happen. So we can calculate the dissipated energy. How? This is a elastic plastic strain, right? And here, yield stress. Let's say dissipated energy equal sigma 0 EP. Very simple. That's just the area of this rectangle. Right? This is dissipated energy. Very simple. And how about elastic energy? Elastic energy equal 1/2 sigma 0 E, right? This is EE. EE. If I sum both, this is a total energy supplied to the material from the outside. Okay? So, this sum of total energy is supplied, but only this amount of energy is stored as an elastic energy, which can be used for reversible process. Reversible process means it can be used for undeformation, undeformed process. Okay? But this energy just disappear. Actually, not disappear because the energy should be conserved. So, this amount of energy is changed, transferred to the heat energy. Okay? So now we can calculate the dissipated energy, right? This is very important, actually. So now let's define some dissipated energy. D is a rate or dissipation per unit volume equal sigma 0 and EP is an elastic strain. This is absolute value. Because dissipated energy is also energy. Energy should be positive, right? So I use the here absolute. And here, because this is rate, I'm going to put that. That means here, that means the derivative of time, dEP, right? Here, okay, this is a plastic strain rate. Right. The reason I use the plastic strain rate instead of plastic strain is that here, once when the stress is a yield stress, okay, actually this plastic procedure is that it's a dynamic situation, right? With some rate. Okay, this is not a static situation. So we need to use a concept of rate. Okay? Okay, and this is actually D is a function of plastic strain rate, right? So, rate of dissipation for unit volume give us how much dissipation happen in the unit volume of the body, okay, during 1 second, okay? Okay, so now let's give you some rule. So S sigma 0. Here sigma S is a plastic admissible stress. So stress should be always smaller than yield stress, right? we are saying that's a plastically admissible stress. We studied about this in the last lecture. So, from this, we can easily find that in this equation, if I multiply the plastic strain rate at both sides, we can find equation this. Simple equation this. So when plastic deformation happens, okay, this amount of plastic dissipation occur, right? And because the yield stress is always bigger than stress, right? Possible, any other possible stress. So it means during the plastic deformation, okay, maximum plastic dissipation happens. So this is named maximum plastic dissipation. Okay. So in other words, we can think during the plastic deformation, the driving force for that dissipated energy is a yield stress, maximum stress, right? When the stress is maximum, plastic deformation happen and plastic dissipation become maximum. So all of these are concepts derived from one-dimensional case and can be used for 2D and 3D case. It can be, all the concepts can be directly extended for general case. Okay, so until now we only talk about one-dimensional stress-strain relationship in elastic and perfectly plastic case, right? Now let's apply this simple theory to structural member. Okay? First, plastic bar. Under that simple plastic material model, let's look at the behavior, plastic behavior of bar. Okay, so here, let's say we have a bar of length L, and which is a prismatic bar, so it has a constant area, A, and P is applied force. In the stress strain level, we have a material behavior like this. Okay, so sigma 0 minus sigma 0 E0 minus E0. So strain E0 means the maximum elastic strain, right? Maximum elastic strain. So this graph can be very easily extended for the bar. So in this bar, important graph is a PE graph. P is a tensioning force, and E is a stretch. This is stretch. Right? So it can be very simply P0 minus P0, something like this. E0 minus E0. E stretch. Here K, 1K equal LEA. Here 1E. So instead of yield stress, here P0 is a maximum. So that E0 is a plastic force, right? So that's the maximum force which can be applied to this bar. Okay? Once the applied force P is bigger than P0, this bar stretched with a undetermined rate. So rate of dissipation in a bar can be calculated by, let's say this is an internal dissipation, can be calculated rate of dissipation per unit volume, and I'm going to, if I integrate this over all the volume. Okay, here let's say P0 can be very simply calculated sigma 0A, right? So all the section, cross section, yield stretch is reached. Then this become volume 0 P dB equal for bar case it become A L sigma 0 and L E P equal A sigma 0 E P equal P 0 E P. So this dissipation means here area of this triangle. This is P, this rectangle, EP. Right? So for this bar case, we can calculate the dissipation, energy dissipation. You know how to drive this here. D. This is from the definition. Okay? And if I integrate this it means just if I multiply AL, this integration can be done because this is a simple bar case. And then this strain can be calculated by this equation, stretch over length, right? Okay, then L go to outside. And okay, so if I multiply this A sigma 0 and we can have a P0. So we can drive the plastic dissipation, rate of plastic dissipation for bar case. Okay, so any question?